Hello everyone, my name is Gauthier Legrand and I work with Sébastien Manneville and Thibaut Divoux at the UNS de Lyon on polymer-carbon black aqueous suspension, and we try to understand this system through a phase diagram. First of all, we use carbon black, which comes from an incomplete combustion of hydrocarbons. It forms this sphere made of carbon atoms that aggregates to form this fractal structure through covalent bonds, which means that this structure is unbreakable. And this is what we refer to the colloidal particle of carbon black. Typical radius is around 300 nanometers, and you can see here a temp picture of this aggregate. The main interaction between these aggregates is van der Waals interactions. So carbon black in water is not something new. It has been already done by a long time ago by the ancient Egyptian, when they tried to make Indian ink out of the soot of a candle, which is actually carbon black. But if you put this in water, you will see that this is not a stable system because carbon black is very hydrophobic, and if you want to stabilize this, you need to put a dispersant in the suspension, which was in this case became a polymer. The mainly acknowledged scenario for this stabilization is the following. So there is the polymer that is adsorbed at the surface of the carbon black particle to decrease the hydrophobic interaction between the carbon black particles and the water. But to our knowledge, there is no experimental proof of this vision, and this is what we aim at in this talk. Also, carbon black in water is not only used for engine ink, and it can be used in flow batteries, which are an improved kind of battery. So the main limiting factor for the power delivered by a battery is the specific surface of the electrode. And if you put carbon black percolated network in the electrolyte, you will observe very high increase of the specific surface of the electrode, which would lead to a higher power delivered by this battery. Finally, carbon black in water has already been a little bit studied in the literature, and people tend to use either a surfactant, for example, CTAB, for which people observe the formation of a double layer of the surfactant at the surface of the carbon black, or LIVZ. In this case, they observed the formation of a yield stress fluid. On the other hand, other people try to study this system with the different kind of polymer, and especially see what are different for different polymer and what are the stabilization scenario. In this study, we will only focus on one polymer, the carboxymethyl cellulose, and we will fix the molecular weight so that the radius of gyration is about 50 nanometers, which is 5 to 6 times smaller than the radius of the carbon black particle. As we are dealing with polymer, we will consider different regime depending on the concentration of the polymer. The first one is a dilute regime for low concentration, where the polymers are independent from one another, and the semi-dilute regime for higher concentration, where polymers are entangled and they interact a lot with one another. The transition between the two regimes is called the overlap concentration, and we note it C star. To evaluate this for our system, we will take a look at the zero shear viscosity that we extract from a cross model of the viscosity as a function of the shear rate for several concentration of polymer. And thanks to the zero shear viscosity, we can compute the specific viscosity. That is the zero shear viscosity normalized by the solvent viscosity, and we plot it as a function of the polymer concentration. You observe here two different regimes. The first is the dilute regime, where there is a linear relationship between the two, and the semi-dilute regime, where there's polar law between the viscosity and concentration, with a typical exponent of 4.4. Thanks to this, we are able to measure to estimate the overlap concentration to be around 1% in weight ratio with respect to water for this specific polymer. So now that we understood the two ingredients of the system, let's mix them in water and see what happens. The function of the polymer concentration or the carbon black concentration. The first thing is, if you put a small amount of both of them, you will observe that the system is not stable because you didn't put enough polymer in the system to stabilize the suspension. But if you increase the polymer content, you will observe a viscoelastic liquid. And then if you increase the carbon black content, you will observe a gel, which means that there is a percolated network of carbon black particles that is formed inside of the bulk. And finally, if you increase even more the carbon black content, you will observe a brittle paste that is very stiff. In this talk, I will only consider the gel phase and keep in mind that the overlap concentration lies like so on the phase diagram. So actually, we will take a look at the gel phase, but you should expect that there are two very different behaviors depending on the concentration of the polymer, because in each regime, the dilute and semi-dilute regime, the physics at stake is very different. So you should expect two different behavior in the gel phase also. The first feature that we want to look at is a recovery after a pre-shear at high shear rate. And for example, we will take a look at the elastic and loss modulus as a function of time after this pre-shear. In the dilute regime, you observe that the gelation time is very short, and we cannot measure it here. And the scaling of the elasticity follows a logarithmic law. For the semi-dilute regime, you observe that there is a very longer gelation time, and the dynamic is faster than a log. So the difference between the two comes from the fact that in dilute regime, the viscosity of the solvent in which the carbon black particles need to evolve to percolate is very less viscous in the dilute regime. So the semi-dilute regime is easier in this case for them to percolate than in this case. Something that is very different between the two is also the typical scale of the elasticity. And let's have a look more systematically. Here we plot the elasticity as a function of the CMC content, and you observe two very different regimes. The first one is whereas the elasticity is a decreasing function of the CMC content, and you observe this can be explained by the fact that CMC screen the interaction between the carbon black particles. This is why there is decreased function. And on the other hand, in the second regime, its elasticity is an increasing function of the CMC content, and it means that the more polymer you put in the solution, the more entangled the polymer are, and so the elasticity should rise also. The transition between the two regimes is very sharp, but it does not occur at the overlap concentration C star, but rather a critical transition of around 0.3%, which is significantly smaller than the overlap concentration. One can argue that the overlap concentration we measured was without carbon black, but actually if you take only into account the volume of the carbon black particle at this concentration, you will get an overlap concentration, an effective overlap concentration of around 0.8%, which is still much larger than the 0.3 critical concentration that we see here. And actually, this 0.3% concentration is very robust, and it seems not to depend on CB content. As you can see here on the map of the elasticity in the phase diagram, you see that for any CB content, the elasticity decreases until 0.3% in CMC content, and then it increases again. So there is something that needs to be understood on this critical 0.3 concentration of CMC. So now that we've understood the two features in the gel phase, we can propose two hypothetical microstructure. The first one, in dilute regime, the microstructure is driven by a colloidal network that is decorated by the CMC polymer to kill the hydrophobic interaction between carbon black and water. On the other hand, for the semi-dilute regime, there is a very dense polymer matrix in which there is an embedded network of CB particles. So now that we have some insight of the microstructure in the gel phase, let's have a look at the linear properties and especially the viscoelastic spectra in the gel phase. So in the dilute regime, you observe that the moduli seem not to depend on the frequency, and you also see that the elasticity is much larger than the viscosity. On the other hand, for the semi-dilute regime, the elasticity and viscosity are all the same order of magnitude, and they exhibit a power law dependence. As the latter is more threatening, we will take a deeper look at this dependent and study how does this depend on the CB content. So if you increase the CB content, you observe two things. The first being that typical moduli increase with the CB content, which is inconsistent with the elasticity map that we saw earlier. And the other thing that is very interesting is that the overall shape of all these spectra seems to be the same, and it makes us really want to create a master curve of all this data. But to do so, we need to evaluate a typical modulus and a frequency scale. But to do this quantitatively, we need a model that takes into account the power law dependence of the spectra. A model that works pretty well is a Kelvin-Voigt fractional model, which is basically a Kelvin-Voigt model in which we replace the dash pot by a spring pot. The constitutive equation of a spring pot is defined by this quasi-property V and fractional derivative here. In the Fourier space, you can compute the complex modulus, and you can observe here that there is a parallel dependence between the frequency and the modulus. So thanks to this three free parameters model, we are able to fit very well our data, and we can also construct two typical scales, G net and omega net. Thanks to them, we can plot this master curve that works also pretty well, and the typical scale lines are actually in a linear relationship, which means that this master curve is relevant. One thing that is still need to be understood is that at high frequency, we should expect to find the behavior of the solvent. But as you can see, the slope here is much smaller than the slope of the pure solvent that we measure separately. One scenario that could explain this is that in the case of a gel, the effective solvent that you observe is more concentrated, which can explain the lower slope in the master curve than in the pure solvent, because the slope is a decreasing function as a function of the CMC content. So now that we've understood the linear properties, let's have a look at what happens if we increase the amplitude and see how this gel yield under an oscillatory shear. So basically, in the two regimes, the overall shape of the strain strips is rather the same. But the main thing that differs from the two regimes is the typical value of the yield strain, which is typically 1% in the dilute regime, which is consistent with the fact that we are dealing with a colloidal-driven system. Whereas for the semi-dilute regime, the typical yield strain is around 100%, which is also consistent with the fact that we are dealing with a polymer-driven microstructure. So we can have a look at this behavior more systematically as a function of the CMC for a fixed CB concentration. And once again, you observe that there is a very sharp transition between the dilute regime and the semi-dilute regime when we observe the loss factor as a function of the strain. And the transition also occurs at 0.3%, which is smaller than the overlap concentration. And whatsoever, the cis-dual behavior is also visible in the map of the yield strain when you see that there is a zone of 100% yield strain typically, and above 0.3% and below 0.3%, the typical strain is around 1 to 10%. So to conclude, we observe that there are two gels that have very distinctive rheological behavior. In the dilute regime, the microstructure is driven by the colloidal particles, whereas in the semi-dilute regime, the microstructure is driven by the polymer matrix, in which there is an embedded network of carbon black particles. And some perspectives that we want to study in the next for the future would be to confirm this microstructure through, for example, scattering experiments. And also something that is very thrilling to us is this non-trivial behavior of the yielding depending on the frequency. So we chose one typical gel and we changed the frequency at which we applied the yield, the strain sweep. So we arbitrarily shifted this curve so that it's more visible, and you observe that there is a continuous change in the shape of the overshoot of the loss modulus as a function of the strain. You can observe, for example, an overshoot here that seems to disappear if you increase the frequency. And so to have a deeper look at this two perspective, we aim at running some rheological measurement to probe only the CB networks, which is the only conductive network in this system. So thank you for your attention. I would be really pleased to get in touch with you, so don't hesitate to send me an email at this address. Thank you very much.